so this will be the second part of the lecture. So here we'll talk about quasi-elastic scattering and what we learned from that. So we start to resolve, what's in, we start to resolve the nucleons so we can resolve momentum distributions. We come up with a model to describe, the nucleons in a nucleus in terms of the shell structure, and we can measure their occupancies. We'll start to observe things too, like nucleons in short-range correlated pairs, which I'll briefly touch on today, and we'll go into more detail tomorrow, as well as transparency. And we'll see hints of medium modifications. We'll talk about what that means. Okay, so this is sort of the modified comic. So he's saying, you're trying to predict the behavior of some complicated system. Just model it as simple object, and then add some secondary terms to account for some complications I just thought of. So this is pretty much what physicists do, right? Like we take everything, and whether it's like an elephant that we're approximating to like a circle, right? So we'll talk about in here different models and what they work well for, and then where they start to break down and what that means. Okay, so first, kind of as a very basic thing in quasi-elastic scattering, we can treat the nucleus as a Fermi gas. And so in this way, you can think of, you have the nucleus, you have all these states, and then you can basically calculate like an initial nucleon energy, so p squared over 2m. You can have a final nucleon energy, which would then be whatever you transfer to it. So this q plus its initial energy, because it's swimming around with some initial momentum. And then you can also calculate the energy transferred by such a reaction, which would then be like your final minus your initial energy. So you get a term like this with your cross component. So this is a really nice description. And what we can also talk about is the Fermi energy or the Fermi momentum of the system. So in a Fermi gas, you can fill it with different particles, and as they occupy all of these different states, then basically at kind of, you can imagine like at absolute zero, that the system, that the greatest momentum of the system or energy would be the Fermi momentum. So this is what we talk about it as sort of also like what it could be swimming around in the nucleus is sort of like a limit, but it's not a limit, but we'll get there. But so what we can expect. So the peak centroid then, when we scatter off of a system that's described as a Fermi gas, as we have this q squared over 2m plus some little epsilon factor, and we'll talk about what that is. But we get this term from up here, right? So this epsilon factor kind of contains basically what's happening from the Fermi momentum. So whatever it's moving, or whatever the particle is initially moving with inside the nucleus. And then the width of this distribution. So if you can think of that this peak centroid of a scattering is this q squared over 2m, then the width is going to be defined, is going to be ruled by this term where you have this initial nucleon that was already swimming around with something inside the nucleus. And then this 2 factor, of course, comes because we're doing plus minus. And so the total peak cross section, then you could start to think of scaling it as the number of protons in the nucleus times the probability of interaction between electrons, protons, and the number of neutrons in the nucleus with the cross section probability of electron-neutron scattering. So this is a really good approximation of the cross section in quasi-elastic scattering, and it works pretty well, but doesn't tell you much about the structure at this point. Okay, so early 1970s quasi-elastic scattering data, we have lithium, carbon, and lead. And so what you see here on the x-axis is the energy transfer of the reaction. This is all for fixed momentum transfer up here of 500 MeV. And so what we find actually, that's pretty cool, just like I said, so the peak width then, right, is this q squared over 2m plus some factor, which we call the separation energy or the average internucleon interaction energy. And then you have this, the width of this then is smeared out by this Fermi momentum. And so I think what's really cool about this picture is that as you go from lithium to carbon and to lead, you see like a broadening of this peak, which you can think of goes back to our idea of the Fermi gas. So you start to fill up with more and more states. So then your Fermi momentum then is a little bit bigger, right? And so you have more of a smearing factor. And so basically they did very detailed measurements. The first measurements were done in a paper by Moniz, which I don't include up here, but he used to be our Department of Energy secretary for a while. And then these were like the follow-up. So this is a very detailed paper where they followed up with a lot of nuclei and were able to confirm that these are kind of what we're seeing. So it's really nice because from a very simple model, we can determine basically the Fermi momentum and the separation energy. And so we can also look at the quasi-elastic peak. So quasi-elastic peak is at approximately x of equal to 1, so Bjorken x of 1. And so you can look at the cross-section on the vertical axis, and on the x-axis you have this energy transfer again. And so basically what you see though is as you go to increasing q squared, the peak is a little bit harder to see because you start to have this creeping in of inelastic scattering contributions. So you can't, it gets harder and harder with increasing q squared to keep what it is that you're scattering on intact, basically. And so, but you can always see it. So we even have many reactions where we've gone to much, much higher q squared and seen up to like, you know, tens of q squared where you can still see the proton. Okay, so now we talk about scaling. So what is scaling? Scaling is a dependence of the cross section on one single variable. So that sounds like a feat in nuclear physics, right? We can make this, we can factorize this all into one single variable. So scaling validates whatever your assumptions are when you decide to say that this is scaling. But then when it breaks, that means that there's either something that we're not accounting for in our assumptions, or there's something we don't understand. So at very moderate kind of regime of q squared and Bjorken x, we would, Bjorken x greater than 1, we would expect y scaling, which means that electrons are then scattering, you can imagine, from quasi-free nucleons inside of the nucleus. So this y variable, you can think of it as like the minimum momentum of the struck nucleon. Now at much higher q squared, then we can expect x scaling, okay, where electrons are then scattering from point-like quarks. And so where x, we'll talk about it more later, what this means, but we can think of it then in terms of the fraction of the nucleon momentum carried by this struck quark in the infinite momentum frame. Okay, so under certain assumptions, then we can rewrite the cross-section as shown here in terms of kind of the elementary electron-nucleon cross-section, and then this f of y, which is depending on this y scaling variable, which is the probability in the nucleus to find a nucleon of momentum component y parallel to q, okay? So y scaling and quasi-elastic scattering reveals that the nucleon, it tells us about the nucleon momentum distribution inside of the nucleus. And so the deviation of the cross-section from scattering of free nucleons basically scales to y. And so we can rewrite that down here. So you can see you have the cross-section with z protons in that interaction and n neutrons in that interaction, and the dependence on the y scaling variable. Okay, so the evidence of y scaling is really, really nice because we have a range of energy transfer as shown here. So the points are kind of hard to see because they all fall on top of each other because it's y scaling. So when you start to get up to this other end, so where y is greater than 0, then you start to get inelastic contributions and it starts to break down. But we should caveat this that there's you know, some assumptions built into this. So this doesn't account for final state interactions. We don't account for internal excitation of the nucleon. We don't talk about medium modifications. There's no inelastic processes. So of course, we're talking about y is less than 0 here is where the scaling is of the cross section. And the full strength, so this is the important part of why y scaling is really useful, is that the full strength of the spectral function, okay, the spectral function is like this probability that you can basically pick out a nucleon with this epsilon separation energy and some initial momentum in the nucleus. So that's its momentum distribution. So this full strength of the spectral function can be integrated for a finite range in Q. And so that's really nice because it gives us some information, like I said, on the momentum distribution, and it works really well. So here's helium-3 on the left, you have versus the cross section, and then you can refactorize it in terms of y, and you can see that everything falls on top of each other, basically, and then you start to have your inelastic contributions. So again, on the bottom, and then you have iron as well. So you can take all this different data and separate it by all the different Q squared, and then you can basically factorize everything on top of each other using y scaling. So it's really, really nice because you can basically describe pretty well what the reaction is going to be like using a single variable. So you can also use the Rosenbluth technique on this quasi-elastic scattering. So when I say AE prime, so we can talk about, we're not measuring anything else, but we can measure the AE prime of the reaction at the quasi-elastic peak. And so the Rosenbluth technique allows us to write basically in terms of this factor sigma. Okay, so we can rewrite the cross-section as shown here, and then it factorizes here into these longitudinal and transverse components, these response functions. And so in this equation, we have the longitudinal virtual photon polarization defined over here on the right in terms of the 3 and the 4 momentum transfer squared and the scattering angle. And we can basically make the basic assumption of plane wave Born approximation. We just have to correct all the data for the Coulomb distortions. So to take this kind of data, then we could do basically kind of what we did before, right? We have like a slope and intercept, and you can just plot it down here versus the virtual photon polarization, and you can measure everything about this variable in terms of defining the cross section, right? We measure the cross sections and then we extrapolate to what they mean. And so this is for iron, and so they call this an LT separation because you have the longitudinal and the transverse components. And so we call this an LT separation. And so, the transverse component response has contributions from other types of effects, meson exchange currents and delta excitations. But the longitudinal response should, in principle, obey what's called the Coulomb sum rule. So if you were to integrate the quasi-elastic longitudinal response function over the full range of energy loss, and where GE is sort of rewritten here, it's a combination of GE and GM for the proton. Then if you normalize this to the proton charge, then you should expect this to be 1. So in other words, you should basically be able to take this integral and get the proton charge of what it is that you're measuring. And so we would expect that integrating the quasi-elastic here anyways, we should basically be counting the number of protons in the nucleus. And so these are kind of some of the data that they take, right, for an LT separation. So you have the longitudinal and the transverse, and then you can integrate it. So that's what we're doing, is we're integrating it. And you should be getting back the proton charge. But the experimental findings are kind of, the jury's still out. So I put a few references here, right? So in one set of experiments, they basically see no quenching. So they see what they call, this thing is climbing and it's going to 1. So this is that Coulomb sum on the vertical axis, right? So they see that everything kind of goes to 1 and they're happy. Job is done, it makes sense. And then other experiments went and revisited all of this. And basically, they kind of add more points and they start to see that no, things kind of don't go to 1. They stop, they plateau before we ever get there. And so the question is, what does that mean? And so there's a lot of different ideas from theory on this, but the general suggestion is that it could be evidence for the modification of these form factors in nuclei. So these form factors we think are all the same, right? So we have GE and GM, and they just tell you about these charge distributions, but somehow these charge distributions aren't what we think they are when they're inside of a nucleus. So they're somehow different. And so that would be indicative then that there's quark level changes inside of a nucleus that we're kind of not accounting for when we talk about sticking a proton inside of a nucleus versus a free proton. So there's definitely, we'll come back to this discussion, but basically this is an important hint because this was a really big hint that if things are really not obeying the Coulomb sum rule, then that's something we don't understand, right? So here's our rain cloud. Okay, so we'll take a step back now. We'll go back to our independent particle shell model. We'll just make our very simple model. So nucleons move in an effective, attractive potential formed by other nucleons. And so there's no other interactions here. No interactions between 2 nucleons, no interactions between 3 nucleons, just that's it. It's just the Hamiltonian can just be written in terms of that particle and its potential, which is inside this well. Okay, and so this works decently. This is a reasonable model. We call it like mean field approximation, that these particles are swimming around. This works decently well below the Fermi momentum. And so the approximation here that we use for this is the plane wave impulse approximation, so PWIA. And so here we go back to our assumptions that we discussed earlier. So we assume that only one virtual photon is emitted and it's absorbed by one nucleon. The nucleon doesn't interact further, so there's no final state interactions. And that means that the missing momentum of the reaction is then equal to the initial nucleon momentum of the nucleus. So if you measure everything. So these are kind of the equations for how we describe plane wave impulse approximation and this assumption, which is really important. So you have this electron comes in, emits virtual photon, scatters, right? We measure the scattered electron, and then we measure the knocked out proton. And you would say that this knocked out proton had some initial momentum and Q. And then we measure P final, and we know what Q is from the electron. And so we can reconstruct the missing momentum. So we have the missing momentum, and we have the missing energy of the reaction. And these are the implications here. So in this way, then you can take the cross section and you can put it in terms of the momentum distributions. So you can take the cross section. This K is just a kinematical factor. So it's just sort of like where your slices of the phase space with your cross section, your EP scattering probability cross section, and then your spectral functions. So spectral functions describe kind of the momentum distributions of these things. And you have basically, this is like the probability of like when you scattered in that reaction that you're scattering off some proton, for example, with an initial momentum of P and initial energy E. So some of the experiments then use the plane wave impulse approximation, the shell model, to scatter from the shell orbitals. And so that's what's shown over here is that, if you had a bunch of shell orbitals that are filled up, right, then you could basically tune your kinematics. You could scatter off everything and you could measure a spectrum. And I know that this picture is really hard to see, but so this was basically a NICAF experiment from a long time ago here, 1993. So you have the different orbitals are basically shown by these different points. This is for calcium 40, and it's at fixed missing momentum is what's shown on this side. And then you have the missing energy is sort of what the separation is, the separation energy between the orbitals. So then you can go to this picture on the right where you can reconstruct the reduced cross section, so the strength of those, right? And you could select like this 1d3 halves over here and this 2s1/2 peak over here. And you could plot it in terms of what the missing momentum spread is anyways. So you can see what these peaks are, and they were able to kind of fit these. They were able to fit these pretty well. So they were able to understand the shapes. Everything kind of makes sense. But what was confusing is that if you sort of integrate that and say, this is how many we saw, for example, if you go here and say, this is how many we saw in each of these, that did not make sense. So if you take like the proton charge of the nuclei divided by the independent particle shell model, and they plot it for each of these nuclei, they were seeing that everything was kind of petering out around 65%. And so they were expecting with their predictions that these orbitals would be filled, and they weren't. And so we were missing protons. We were missing proton strength, basically. And so the question is, where did the protons go? So they're here. So, okay, so the vertical axis over here, you can think of as like the density, the proton density in the nucleus, okay? And then this peak right here is our Fermi momentum. And so, prior to this kind of measurement, we expected that nothing should be above the Fermi momentum. So we would think that we wouldn't see any protons in those orbitals above there, but they actually are. They're occupying higher states. And so they found these are the ones in the valence orbits, and then they basically found a bunch of them when they looked in orbits that they didn't expect to see. So different missing energy, missing momentum combination, right? And so this was a very interesting result because this told us that, this kind of was like shooting down sort of just that these particles are just floating around in the nucleus and not interacting or anything. So how are they getting out to this high momentum tail, as we call it? Yeah. Anybody have a question on that? Answers, questions, I'll take both. Okay, so the nuclear picture, though, is a many body problem, right? So they're not sitting in the nucleus and not interacting with each other. I mean, that's how, we already know that it's the residual interaction anyways is what's also the strong force that's binding the nucleus. So from elastic scattering, we already know that quarks and gluons compose the nucleons. And so we can simplify this picture by describing the effective NN interaction. So we use effective interactions a lot of times to simplify things, where we just say, oh, there's a proton and neutron, they're exchanging pions, and that's how they're bound together. But you have what's called, but they live in this NN potential. So this nucleon-nucleon potential within the nucleus. And so you have this potential, you can see it here, it's just kind of abbreviated, but you basically have a strong repulsive core. So you can think of at this end is where you would have two nucleons that are literally overlapping each other, right? Because this is R, this is the radius, and like right about here is the proton radius, somewhere in here. So here you would have two nucleons overlapping each other, and here you have two nucleons playing ball, playing meson, fetch, whatever you want to call it. And so you have the repulsive core, and then you have this attractive part, and then you also have this short-range tensor attraction between the nucleons. And so this is so there's a lot of models and a lot of studies on this, and it will come back tomorrow. We'll talk more about this. But again, repulsive core, they're overlapping. Long range, they're out here exchanging a meson. Then you have two, so here you have basically just the long range part and the repulsive core. And then these are different models for different NN potentials. And again, you can think that the radius of the proton is somewhere kind of right in here. So you can really see why these guys are overlapping each other. And it's interesting because they're overlapping each other. And then this is like a whole branch of study that a lot of people are very excited about because it might answer other questions. So we have nucleon-nucleon short-range correlated pairs. We have nucleon pairs that are close together. So like I said, overlapping the nucleus, and they have a very high relative momentum and a low center of mass momentum. And so the idea is that this high relative momentum, so they kind of, they're doing their tango and they throw each other apart. And that is what's occupying these higher momentum states that they found in this other spectroscopic experiment. But we'll talk all about this tomorrow because this has lots of implications for other QCD features of what we're studying with the nucleus. And so another topic that we have to kind of understand when we're talking about how good our models are and how well we understand them is in quasi-elastic scattering is the nuclear transparency. So we defined the nuclear transparency is basically just the probability that a proton like survives to get out of the nucleus. Okay, so not all protons, you don't knock them all and they all just escape and you can measure them. Some of them are absorbed, deflected. And so we can measure basically the transparency, and it's different for different nuclei because, as we already saw previously, different nuclei are bigger, they have more particles, different interactions. And so we're dominated at high energies by reduction of flux when hadrons propagate outside the nucleus. So we'll also talk about this tomorrow. So that's kind of a brief overview of quasi-elastic scattering. The nuclei are pretty complicated systems, but we model them with different assumptions, and then we use those assumptions where they work. The Fermi gas model gives us a lot of information about cross sections and Fermi momentum and separation energy. We can use scaling, so to refer to the dependence of a cross section on one single variable. So this is kind of used in different places in nuclear physics, but Y scaling works really well in quasi-elastic scattering. So we also have indications that the nucleons that we scatter off in quasi-elastic scattering are not actually quasi-free. So we have both the Coulomb sum rule and this loss of spectroscopic strength in the orbitals that would indicate that they're not really just floating around in the nucleus doing independent things. So some tools that we have anyways to probe these ideas is the NN interaction. We can certainly scatter on particles that we think came from NN interactions, and nuclear transparency. Major backgrounds, so you have inelastic contributions. That's probably the big one. There's actually quite a lot of backgrounds. So I think we'll go into detail on those tomorrow, but you can have like excitations You can have meson exchange currents. You can have a lot of things that look like this, and then you have to kind of exclude those things by the plane wave impulse approximation works reasonably well here, where you can kind of assume that when you knock this out, that its momentum is what it was in, like not the measured momentum, but the reconstructed missing momentum is what it was in the nucleus. So you can start to make kinematic choices in your selection of what it is that you measure. So your kind of your data reduction, I guess, and you can start to rule out some of the other things that look like this. Yeah, so you can also go to certain Q squared where certain effects are less and certain X. So, but yeah, they're backgrounds. Okay, so then we'll talk about deep inelastic scattering. Okay. So deep inelastic scattering, here we're smashing the proton, it breaks up into a many particle final state. Here you have structure functions, and we'll talk about the EMC effect. So we have this idea of the quark parton model. So DIS is dominated by the scattering of a single virtual photon with a point-like spin half constituents of the proton. So these two pictures here, for kind of the purposes of what we're doing, can be, they're related, right? So we can scatter from a proton and describe that reaction with the structure functions. So in this case, we replace the form factors with structure functions, and we can use that to talk about what's going on with the partons in the nucleus. Or you can also think of it as sort of quasi-elastic or elastic scattering from a point-like quark inside of the proton. But of course, then it's gonna, quarks hadronize, so you're not just measuring a quark. Yeah, and then this works sort of in the frame where the proton has very high energy, so we call this the infinite momentum frame. And so, like I said, so form factors are replaced by structure functions with the dependence on both Q squared and X. So they're kind of defined here, right? So you have F1 is sort of more of a magnetic structure function, F2 is electromagnetic structure function, and these aren't the Fourier transforms of the charge distributions like we talked about before. These are more related to the momentum distribution of the quarks inside of the proton. So that's what we think of. And so we talked about scaling, right? So in scaling, we make certain assumptions, and we see that the cross-section only depends on one variable. And so experimentally, these structure functions are determined. So they can be determined with measurements by varying both the scattering angle and the beam energy. And we can observe that these are kind of nearly independent of Q squared, right? Certain assumptions, okay? It breaks down in certain places. So then you can rewrite F1 as F1 of X and F2 of X. So these are a series of very famous data from Hera where you have, this is the F2 structure function because they're actually related to each other. So you can plot the F2 structure function. This is all for different slices of X, which is probably impossible for you guys to read from the back of the room, but largest X is at the bottom, that's 0.65, and then it goes up to e to the -5 at the top, okay? So you can see that these are pretty flat, okay? So this is Bjorken scaling. You can see that as we go to small x, and you start to increase Q squared at the bottom, you kind of lose that, the scaling, right? So it's violated. And so that is basically kind of interpreted as, as we go to smaller x, then here and higher Q squared, we're resolving not just the valence quarks, but something that's sharing more of its momentum with probably the gluonic contributions. Okay, so that's why the scaling kind of breaks down up here, but it works pretty well for intermediate x. And so that's, that's useful to know. So x, of course, we think of in this way that it's like the fraction of the proton momentum carried by the struck quark. And so we have these parton distribution functions where you can think of it as the number of quarks of some type, so like an up quark or down quark or something like that in the proton with a momentum, of x of the proton. And so these structure functions are related then to the quark distributions. So F2 is like 2x of F1, which is basically like a summation over all of the quark types inside the proton. And so this is the Callan-Gross relation. So anyways, these are related. And so you can think of, if you take this parton distribution function on the vertical axis here, and you think of just scattering where x of 1, you're just scattering off of a single proton, right? So you're not really resolving anything. But then you can think of, if you could scatter off a single quark inside of the nucleus, then you could, that's not interacting with anything else, then you would be scattering off of valence quarks. So that would be like 1/3 of the proton momentum. But we know that the quarks are actually doing stuff in the nucleus. They're interacting with each other. And so then you start to get kind of a smearing here because of the gluonic contributions. And then, of course, we know the picture gets much closer to something like this, where you have, you sort of have a falling peak at 1/3 because of the valence contributions, but you have this huge spreading because of all this gluonic contributions from the C quarks and valence quarks and higher order interactions. So we know that, anyways, the picture of the nucleon is pretty complicated space, and we know this pretty well from deep inelastic scattering. Okay, so you can think of taking these distributions, and for some fixed Q on the x-axis, this is x, right? So the valence quarks, you can see here, there's the down quarks and the up quarks, okay, for proton. And you can see that they dominate anyways in this region. So from 0.3 to like 0.7, 0.8, I mean, that's pretty much the big contribution, right, is up and down quarks. And then you start to move to much smaller x, and then you're seeing big contributions from strange and charm and other things, and gluon. The gluon contribution is huge. So keeping this picture in mind, what happens when we scatter from 0.3 to 0.7 in x? You would expect that we're all just looking at up and down quarks, right? And so this is the EMC effect. So recall in deep inelastic scattering that we take the cross section in terms of the structure functions, right? And that's what's shown here. So just F1 and F2. And these structure functions describe the quark momentum distributions. So the European muon collaboration in like the early 80s was the first to observe that the DIS cross-section ratio of a heavy nucleus, so here they took iron versus deuterium, and they divide them by like the number of nucleons, it's not 1. So they were expecting that these things should be the same, right? So we don't expect that they should be different. So here's Helen of Troy here, the face that launched 1,000 ships or 1,000 experiments and papers. And so follow-up experiments showed that these have a universal shape for all nuclei, for a range of nuclei. So this was an important result from SLAC. And then, shown here on the right is that it's roughly Q² independent, actually. So again, it's in this X range from 0.3 to 0.8, and you still have this decrease here. So the broad interpretation of this that I don't think people disagree on is that the parton model interpretation is that the valence quarks of a nucleon, in a bound nucleon, they carry less momentum than those in a free nucleon. But the question is why? So nobody knows why. So the EMC effect can't really be described with just conventional nuclear physics. And so there's many, many theories, and theories are good, and then they have drawbacks in other areas of how these structure functions are modified or how they can be better written. And so this is many experiments, theories, and papers, and we'll talk more about this tomorrow because it relates to other things that we've kind of already talked about. So this is basically kind of our summary then on deep inelastic scattering. So we have the structure functions contain the quark momentum distribution information, density information. And in this model, we can think of DIS as scattering from a quark. And so the momentum that they carry is different in a bound nucleon versus that in a free nucleon. And so that's kind of where we're at, because that's kind of a very profound observation. So again, we go back to, this was our plan, right? We're just going to understand this guy and everything's makes sense. And the reality is that there's different types of experiments and tools that would tell us that things are not kind of what we expect, right? So we can learn from them, and we have to figure out what they mean. And so that's why there's other experiments right now that are going back and doing this Rosenbluth and polarization transfer form factors. And then we have the Coulomb sum rule. We know that there's protons above the Fermi momentum now. And so that's, okay, there's a big description of that, maybe with short range correlations. And then you have the EMC effect. So the summary of the physics at this point is that the strong interaction rate that binds the nuclei is the residual from the strong interaction between the quarks. And we have different types of scattering tools that tell us about different parts of the structure of these nucleons. So that's kind of where I leave you today.
So now we have some time for questions.
Mm-hmm.
Is that
that curve? No, not off the top of my head. There's, I mean, I don't think that's a fit. I think there's different predictions that they try to do different things. We'll talk about the models more tomorrow, but they try to do different things with the predictions to kind of see if they can include the effects we see in the data.
more questions?
I'm trying to understand how was the missing momentum equal to the initial momentum of the ion.
Because it basically comes from this assumption that the virtual photon is absorbed by one nucleon. So if you think this final state, this final momentum of this proton is like whatever the initial one was, plus whatever momentum was transferred to it, right? So it was doing something, you hit it, and then you add the two vectors, basically. And so in this reaction, then, I mean, we're not smashing anything apart. So, so basically you could rewrite this as like Q minus, so anyways, you can take PI equals, we take the minus sign, depends on where your X is, but you can take, it's the difference between the Q and the PF, and you get the missing momentum of the reaction. So it's just whatever's lost, which is on the order of a couple, depends on the reaction, couple 50 to 100 MeV or something like that, typically. For mean field.
So let's think Holly again, but think around